So in this question, we have a central angle that measures 40 degrees inside a circle. The radius is 15 centimeters. We're supposed to calculate the area of the sector containing the central angle. We'll get to that in a second. But then we also need to calculate the area of the segment formed by the chord joining. So there's a lot in this question. I'm going to start by drawing my angle here at 40 degrees. It's not going to be exactly 40 degrees, but hopefully we get the idea here. So here is my sector that I've just created. And we know that the angle in here is 40 degrees. And when we calculate the area of the sector, we're trying to find the area of all of this right here. And just a reminder, that sector is a portion of the circle. What we're going to do is we're going to figure out what fraction of the circle it is, and then take that fraction of the area. So the area of the sector is equal to whatever fraction of the circle it is. Well, that's 40 degrees out of the 360 degrees that there are in a circle. So we've got 40 out of 300, and then we're going to find the area of a circle. So the area of the circle, is pi times the radius squared. We are told that the radius is 15. We can add that on our diagram here as well. So pi times 15 squared. And if we plug that into, we can simplify this if we wanted to. 40 out of 360, we could divide numerator and denominator by 10. That's 4 out of 36, which is 1 out of 9. Or we can plug this directly into our calculator. And when we do that, we will get an answer of 78.5 centimeters squared. So that's the area of the sector. That's this part right here of the question. So we've done that part. And now we need to calculate the area of the segment formed by the chord joining the two base points of the central angle. So that chord, let's see if I can draw the chord in here. Maybe do it in green. That chord looks like this. And when we calculate the area of the segment, I'll highlight that in a different color. So that's this area right in here. So in order to find that area, what we're going to do is we're going to take the area of the sector that we just calculated, the area of the segment, is equal to the area of the sector minus the area of the triangle. Well, we already have the area of the sector. Now we just need to find the area of the triangle. Here's how we're going to do that. We're going to start by drawing the line from the center of the circle to the chord. That line will bisect the chord and create two congruent triangles, two triangles that are exactly the same. And those triangles will have the property that this angle here will be 90 degrees. The angle in here now will be half. The angle in here will be half of what it was. We just cut it in half. We bisected the angle. So maybe what I'll do is I'll draw that triangle out here so we can get a good sense of what's going on. This line, the hypotenuse of that right angle triangle is the radius of the circle. It is a right triangle, so we know that this is true. And the angle down here is 20 degrees. So again, looking at our big triangle, the height of that triangle is going to be this right here. So I'm going to call this H. So let's find H. So this is our work for finding the area of the triangle. This is a right angle triangle. Let's see if we can just kind of label it a little bit here. Here's the hypotenuse. Here's the adjacent side to that 20-degree angle. And so maybe I'll back up a little bit. Using trigonometry, we want the adjacent side. We have the hypotenuse. We're going to use the cosine ratio. So the cos of 20 degrees is going to equal the adjacent side, which is H over 15. Multiply both sides by 15 to find H. And if we plug that into a calculator, again, make sure your calculator's in degrees, otherwise your answer will look kind of funny. And I think here, if we do that, we'll get an answer of 14.1 centimeters. We can see that it is less than the hypotenuse, which makes sense. So this is the height of our triangle. It's the height of the little triangle that we kind of took out here, the little right angle triangle. It's also the height of this bigger triangle inside the sector. Once we have the height, we need the base of this triangle. So the base is like this distance. At the risk of kind of muddying up the diagram too much here, we'll try this. We need the base, this distance across here. So let's start by finding, I'm going to call it x, just for lack of a better term. We'll find this distance right here on our smaller triangle. And we can do that with trigonometry. We could do that with the Pythagorean theorem. I'm going to use the Pythagorean theorem. So we know that x squared plus the height, which is 14.1 that we just calculated, squared has to equal the hypotenuse squared, which is 15. 14.1 squared is 198.8. 15 squared is 225. And now subtract 198.8 from both sides, and we get that x squared is equal to 26.19 approximately. We'll call that 26.19. We'll take the square root of that, and we get approximately 5.1. Now remember, that's the distance here on our small right angle triangle. We want the entire distance, this sort of brown highlight here, all the way across. Well, there are two of those. So the base of our triangle, base of our big triangle, is equal to 2 times that 5.1 value, which will give us 10.2 centimeters. So really what we have now, I'll just draw it out again so you can see what we're doing. We've got this triangle here. It is an isosceles triangle. We know that the sides, two of the sides, anyway, on that triangle are 15. We know that the base is 10.2. And we know that the height is 14.1. So now we can find the area of that triangle. So the area of the triangle is equal to 1/2 the base times the height. Base is 10.2 times the height, which is 14.1. Let's try that again. And if we plug that into the calculator, we should get 71.9 approximately centimeters squared. Just a reminder that the area of the segment is the area of the sector minus the area of the triangle. So here's the area of the sector. Here's the area of the triangle. We want to subtract those two to figure out the area of the segment. So let's go ahead and do that. So the area of the segment I'll write this again just as a reminder. Area of the sector minus the area of the triangle, which is 78.5 minus 71.9. Subtracting those two, we get approximately 6.6 centimeters squared. So the area of the segment, maybe we'll just write a concluding statement. The area of the segment is about 6.6 centimeters squared.